Hey everyone, in this lecture we're going to be discussing multiplying generating functions and partial sums. Now, what exactly happens to sequences when you multiply two generating functions? What do I mean by that? Well, let's take a look. This is going to look a little messy, but just hang in there. Let's say we have a generating function a, which is a0 plus a1x plus a2x squared, and b, which is b0 plus b1x plus b2x squared plus, and then so on. So to multiply a and b, we need to do a lot of distributing. In fact, it's kind of like foiling, but an infinite number of times. But keep in mind, we can group together terms, and we only need to write down the first few terms to see a pattern here. Let's take a look about what I mean here. Let's multiply a and b. So a times b is a0 plus a1x plus a2x squared, and then so on, times b0 plus b1x plus b2x squared, and so on. So when we FOIL, when we do a bunch of multiplication across here, let's take a look at what happens. Well, what would the constant term be? We know this is going to be a polynomial because when you multiply two generating functions, you get a generating function. And so we know this is going to have some sort of like constant term. Now, what would the constant term be? Well, when we FOIL, when we multiply each term by all the other terms of the other generating function, you'll notice that you'll pretty much always get an x. For example, this term multiplied by any term here is going to have an x factor in it, at least. So we know that this number, right, this expression is not going to contribute to the constant term. Likewise, multiplying that by every single term here is going to give a factor of x squared, which is not going to contribute to the constant term. So to get the constant term, the only way to do that is to multiply the constants here, a0 and b0. And in fact, the first term in this generating function would be a0 times b0. What about the coefficient of x? Well, the only way to get x would be if we multiply, let me erase this so that I don't confuse anyone. The only way to get exactly 1x is if you multiply that term by that term. That gives you only 1x. The other way is if you do a0 and b1x. That's another way. So there are two ways of getting just 1x, exactly 1x. And so the coefficient for x would be a0 times b1 plus a1 times b0. What about x squared? Well, in that instance, we could do a0 times b2x squared, we could do a1x times b1x, or we could do a2x squared times b0. So this would be a0 b2 plus a1 b1 plus a2 b0 x squared, and so on. Can you see the pattern here? So what do you think the coefficient would be for x cubed? Well, seeing this pattern, we can probably guess it would be a0 b3 plus a1 b2 plus a2 b1 plus a3 b0. And so on. You could keep going with this for this multiplication. Hey everyone, real quick, I just want to mention that this video is a part of a whole course that I made. You can find a link to this entire course in the description below, and make sure to click on that subscribe button. All right, let's actually do an example together to see what this looks like. I have a prepared example. Let's multiply the sequence 1, 2, 3, 4 by the sequence 1, 2, 4, 8, 16. Now, it's technically a little weird to be multiplying sequences. That's not quite well defined. But that's why we put quotes in the multiply word here. The constant term when we multiply these would just be 1 times 1. It would be that times that, 1 times 1. Okay, the next term would be 1 times 2 plus 2 times 1, which, by the way, is 4. The next term would be 1 times 4 plus 2 times 3 plus 3 times 1, which, by the way, is 11. That would be the third term in the sequence. Let's do one more. This one's going to be a little bit extensive here. This would be 1 times 8 plus 2 times 4 plus 3 times 2 plus 4 times 1. It should be a plus. 4 times 1, which, by the way, is 28. And we can just keep going here. The resulting sequence would be 1, 4, 11, 28, and so on. That's what we mean by multiplying sequences. Since the generating function for 1, 2, 3, 4, this one right here, is just 1 over, here, I'm actually going to erase all this. Since the generating function for the first one is 1 over 1 minus x all squared, and the generating function for 1, 2, 4, 8, 16 is 1 over, I believe it's 1 over 1 minus 2x. Yeah, 1 minus 2x. We have that the generating function for that sequence, 1, 4, 11, 28, 57, and so forth, that we just found, is just the multiplication of these two things. So we can multiply these. And that's the resulting generating function. Consider the special case when you multiply a sequence by 1, 1, 1, 1, 1, 1, 1, and so forth. For example, multiply these two sequences. Let's do 1, 1, 1, 1, 1, so on for the first sequence. And let's do 1, 2, 3, 4, 5, and so on. The first term, if we multiply these two sequences, would be 1 times 1. Then the second term would be 1 times 2 plus 1 times 1, which, by the way, is 3. The third term in the sequence, after multiplying these two things, would be 1 times 3 plus 1 times 2 plus 1 times 1, which is just 6. And then the next term would be 10, and so on. We are getting the triangular numbers. More precisely, we get the sequence of partial sums of 1, 2, 3, 4, 5. In terms of generating functions, we take 1 over 1 minus x, which is the generating function for 1, 1, 1, 1, 1, and multiply it by 1 over 1 minus x squared, which is the generating function for 1, 2, 3, 4, 5. And this gives us 1 over 1 minus x all cubed. This should not be a surprise, as we found the same generating function for the triangular numbers earlier. The point is, if you need to find a generating function for the sum of the first n terms of a particular sequence, and you know the generating function for that sequence, you can multiply it by 1 over 1 minus x. To go back from the sequence of partial sums to the original sequence, you look at the sequence of differences. When you get the sequence of differences, you end up multiplying by 1 over 1 minus x, or equivalently, dividing by 1 over 1 minus x. Multiplying by 1 over 1 minus x gives partial sums. Dividing by 1 over 1 minus x gives differences. And this is extremely useful when applying generating functions, which we'll show how to do in a future lecture. Thanks everyone, and I'll see you in the next video.